for today. Thank you for your message. To start, Holy Spirit, we ask and pray, grant us wisdom, understanding. In Jesus' name. Amen.
Amen.
All right. Now, concerning this extended, we've treated. This is the question we started with, the one I sent to you guys.
Okay.
Okay, we started off with this. I guess that was before you came. That was the last time in class. So, but since you're the one here, let's go through it again. Um, the question here says a car accelerates from rest at time zero and its maximum speed. Figure 1.1 is a speed time graph of the first 25 seconds of its motion. The mass of the car is 2,300 kg. For the time t is equals to 0 and t is equals to 5.0, determine the acceleration of the car. Okay, do you have any idea of how to do this?
We have the what do you call this thing? We're looking for acceleration. Acceleration is not that equations of motion, that v minus c over t stuff.
Okay, that's okay. V minus u over t, right?
Yeah.
Okay, yeah, that's acceleration. That's acceleration. So all we just need to do is v minus u. That's the first thing. Is equal over t. Now at time t is equals to 5. You might need to. Do you have that script with you?
Yeah, I'm with the script. I was doing the
Okay.
OBJ, but I haven't started the theory.
Okay. Now let's look at this. Look at this 5 here at time t. Now and look at this point here. What number is this? This should be 10,
15.
15, right? So
Yeah.
okay, so that makes it good. That becomes 15 minus what's the initial velocity?
It's not 0.
Yeah, 0 because it started from rest. 0, and that's t is equals to 5. So that means the answer is 3 meters per second square. Okay, so that's the answer for that.
Okay.
The next one is they said the resultant force acting on the car. How do we get force? What's the formula for force?
Mass times acceleration.
Exactly, mass times acceleration. So that becomes, remember your formula is key, mass times acceleration. Remember they gave us the mass as, I think the mass was
It's
given
up
as
there.
2,300.
2,300.
Okay, 2,300 times 3, and that is sorry, I use your
6,900.
calculator.
No, I use my head. 6,900
6,900 what?
joules.
No.
It's not force. Oh,
Yeah,
Newton.
force, Newton.
Which
Okay,
one is joules? Energy.
energy or work.
Okay.
Yeah. Okay. Now, if that's the case, the next one is I hope you're writing them right.
Yeah.
Okay. The next one is describe the motion of the car. T is equals to 10 seconds and 15 seconds. Okay. They said explain. Okay, shows this. Okay, let's describe the motion of the car from 10 to 15. What is happening?
Is it seconds or?
Yeah, from 10 seconds to 15 seconds. Well, actually, the first thing you're looking at is the shape.
It's
So
curving now.
now, yeah, it's curving. What's 10 to 15 seconds? Actually, this is what you're looking. You remember when I taught you guys velocity time graph? I told you that
Yeah.
every part of the graph means a lot. every part of the graph. So from this point of your graph to this point of your graph, now what is happening? They need you to explain this point of the graph. What happened to the graph at this point?
Is it not constant or is it that constant or uniform acceleration?
No, it's not uniform acceleration at that point.
So
The,
constant.
at that point, remember, I if you're looking at uh, if you could remember when I told you guys, um, when we look at curve, when it's going like this means that there's an increase in acceleration, and when it's going like this, it means that there's a decrease. So it's decreasing. There's a decrease at this point now. It started from rest, went to constant acceleration. Now, at this point, it was about increasing. Now, at this point now, there's an increase in speed or increase in acceleration at a decreasing rate because it's about decreasing. But at this point now, there's a slight increase. There's a slight increase in acceleration. So that's what is happening there. It's just from 10 to 15. We just want to know what's happening there. So there's a
Increase
slight,
in acceleration.
so what's happening there, it's the the velocity, sorry, is increasing, but the acceleration is decreasing. The velocity
How
of
is
the car,
acceleration decreasing?
sorry?
So how is acceleration decreasing?
Okay, look at this now. For example, let's take this point now. I'm going to explain this. Um, Look at the height of that 15 is close to 30, right?
Yeah.
Now, I want to take this is speed, this is time.
Mm-hmm.
This is velocity, this is time. Now, 30 divided by 15 is what?
2.
30 divided by 15 is 2. It's okay. Now, let's take um, the speed or the acceleration at this point when it's 20 when t is equals to 10. What is speed at this point?
Should be 25.
25. Okay, so 25 divided by 10 is what?
Divided by 10.
Yes, at this point, that's
2.5.
2.5. So you see now that the acceleration just decreased from 25 to 30. Acceleration is 2. It was at 25, it was 2.5. By the time it got
Oh
to 30,
yeah, I
what
see
happened to
it.
acceleration now? It became 3.
It decreased
Yeah, I'm sorry, it became 2. It decreased, right?
2.
It decreased. So what is happening is that the speed is increasing, but acceleration is what? Decreasing. Did you get that now? Hello?
Yes.
Yeah. Did you get that?
Hi.
Did you get that explanation now? Hello?
I'm here. I'm writing it.
Okay, okay, okay. Now let's start with the next one.
Next one.
Okay. The next one now is between t is equals to 10 and t is equals to 15. The force exerted on the car due to the engine remains constant. Between T10, the same T10 and T15, the force exerted on the engine remains constant. Suggest and explain why the car moves in that manner, in that way, okay? Let's come back now. Suggest why the car will curve towards this direction. Suggest why the car will move in that direction, okay?
Maybe it says the force remains constant. So I don't know. Maybe it's slowing down or something.
Okay. So what kind of force do you think will cause the car to move in that direction
Direction.
or in that manner? What do you think? What kind of force do you think will make the car move in that manner?
I don't know. Maybe drag or air resistance. I don't know.
Yeah, air resistance. Air resistance. Air resistance is a factor of making air resistance and friction,
Oh
friction,
yeah.
friction, friction between the tires and the car and the road, the tires of the cars and the road. So friction would definitely increase friction, air resistance. They would likely be the cause of that. So that's the end of that question. Okay. Now coming to the next one. Were you there when we did this?
No.
Okay. Um, 2A, state two properties of an object that may be changed by the action of forces. Okay. That means what it's trying to say is state two what force can do to any object. The likely
Can you
things
change
force
the
can
weight?
do. You said?
Can you change the weight?
It can change the size. When force is applied to an object, number one, it can change the shape. It can change the shape of the object. It can also change the size or the volume of the object. Okay? It can change
Okay.
the shape of the object. It can also change the size, the volume of the object. It can even change the direction of motion of an object. For example, when force is applied to a car or to a ball, it changes the direction, it changes the speed, it changes the velocity of the ball. Why? Because there's a force coming from the leg of someone or yeah. So that is it. Okay,
Mm-hmm.
B. A chest expander is a piece of equipment used by athletes in a gym. Figure 2.1 shows a chest expander that consists of five identical springs connected in parallel between two handles. Each spring has an unstretched length of 0.63 meters. Two athletes are stretching the chest expander by pulling on the two handles in opposite direction. The spring obeys Hooke's law. So explain what is meant by this statement. What is Hooke's law?
Um, Forgot.
Okay. Hooke's law states that provided elastic limit is not exceeded, the force acting on an
Is
elastic
directly
material,
proportional to
yeah, the force
the
acting on an elastic material is directly proportional to what? Is directly, pro-
forgotten. I just was provided the elastic limit has not been reached.
yeah, provided the elastic limit is not exceeded, the force acting on an elastic material is directly proportional to its extension, provided the elastic
Oh,
limit is not exceeded. So that means F is equals to KE. So where F is in Newton, E is in meter, so K, the constant of proportionality, is F over E, which is Newton per meter. Okay, so but this should be added to your um.
write the formula.
You said
I should write the formula.
yes, but that's after you have said the hook. You've given the Hooke's law. You stated
Okay.
the you've given it. The force acting on an object or an elastic material is directly proportional is directly proportional to the extension provided the elastic limit is not exceeded. Provided the elastic limit is not exceeded. Okay, have you written that?
Yes. Which formula am I writing? F equals to KE.
Yeah, F is equals to KE. You can put F is directly proportional to E, then F is equal to KE.
Yeah.
Okay. Now the next one is Michelle. Michelle, are you active here? I've been asking her to unmute. I don't know what she's still doing. Oh, okay, Michelle, please, if you
I
can
see
hear
on the
me,
card.
unmute yourself. Okay. Let's continue. The the next one
I'm
is
active.
okay. All right. Now the next one is state each athlete pulls the handle towards himself with a force of 1,300 Newton. Okay. Remember, this is the question we are looking at. Now they said each athlete pulls the handle towards himself with a force of 1,300 Newton. State the tension in each spring. But if you go back to the question, one thing I've noticed with IGCSE questions are if they ask you a question, always learn to check all these things. They are really important to you. These things are very, very important. Look at where they said again. Look, and for you to answer that question, you need to take note of these things they said. Number one is a chest expander. Number two, five identical spring. And you take note of this. You also take note of, yeah. So we've taken note of these things now. They said each athlete pulls, each athlete pulls the, where is it? I'm coming. Each athlete pulls the handle towards himself with a force of 1,300 Newton. So what would be the tension in each spring? What would be the tension in each spring? Any idea?
Isn't that
You said?
the isn't not supposed to be the force over the length of unstretched distance?
No. They didn't ask. Remember, they're asking you for tension. Tension is similar to force. Tension is is also the force. It could be tension, it could be force, it could be load. They are all measured in Newton. So you can't if you divide it over this, that means you are already getting the constant of proportionality. But that's not what they asked us to find. What
Oh,
they asked us to find was tension. Okay. So what you look at the answer to that question is embedded in this. There are five identical spring. Now they are asking you what is the tension in one spring. Have
oh,
you have you gotten the idea now what I'm
since
trying to say?
yes, since we have if the force, like the combined force, do we divide
Yes.
it by 5?
Yes, exactly. They already said each athlete pulls it with a force of 1,300 Newton. So they already have 1,300 Newton. Now they are pushing this. What is the force in each spring that makes them equal? Because they said the springs are identical. Whenever you mean they're identical, that means they have similar weight. Everything are similar forces. They are being pulled with similar forces, right? So,
Yes.
so with that now, with that, all you just need to do is 1,300 divided by 5.
260.
You said?
260
Yes. So divided by 5, and that gives you 2, 260 what?
Newton.
Yeah, Newton. That's it. Okay. Now, the next one is the chest expander stretches, and each spring is now 0.94 meter long. Each spring is now 0.94 meter long. Calculate the spring constant of each. Now, I didn't give you this formula also, that E is equal to, that's the new length minus the original length. Okay, so
Okay.
if you have this in mind, if you have this in mind, can you get the first can you get the first constant? The first thing is to do is, your first constant is F over E, right?
Mm-hmm.
Okay, so what is your force? Remember, we are looking in
260.
each spring, that is 260. Okay, what is your E? Your extension.
0.31.
Well, how did you get 0.31?
I did this 0.94 minus the this thing that they gave us before.
Exactly. So that's 0.94 minus the unstretched spring is 0.63, right?
Yes.
Okay, 0.63, which is okay. So tell me, 260 over that will give us what?
838.71.
Um, 838.71.
Point
838.
seven one. Yeah.
Okay, 0.71. Now, what's the unit? Remember, follow this. Force is measured in
Now,
what?
does it?
Force is measured in what? Follow this formula now. Force is
First
measured in what?
constant mistake.
Yeah, no, it has a unit. Force is measured in what?
Newton. Please.
Force is measured in Newton slash what is the unit of extension?
Hmm?
What's the unit of extension? Okay, extension is measured in
Meter.
what? Meters. So this is the unit. Newton per meters.
Okay.
Okay. Good. Now let's continue. State the energy changes taking place as the two athletes use their muscles to stretch the chest expander. Okay, so let's go back again. What kind of energy changes are taking place here? What energy changes are taking place here? Now, you must look at the fact that they are using their muscles here, right? They're using their muscles. They're using their muscles, okay? And they are stretching this part. So what the energy that has to do with you using the cells of your body is called what?
Hmm?
Energy that has to do with you using the cells of your body.
I don't know.
Yeah, okay. Can I ask you this question? Do you know that if you don't eat, you won't have the energy to pull this? So, what is the energy derived from your food?
Um, chemical energy. I don't know.
Sorry?
Is it not when you eat you get chemical energy
Yeah,
stored in your body?
it's chemical energy. So, chemical energy is also gotten from the cells of your body. That's chemical energy. Now,
Mm-hmm.
what this kind of energy now that is being pulled in this spring is what?
Elastic.
Yeah,
Elastic.
elastic potential energy. Okay, elastic potential energy. So, coming
It's
here
chemical
then,
to
so from
elastic
chemical
potential.
energy to elastic potential energy. Okay, chemical energy to elastic potential energy. All right, let's continue with this.
Is there anything like elastic kinetic?
No, 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 elastic
So is
potential.
there anything like elastic kinetic?
No, 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 elastic potential. There's
Okay.
okay. Now is actually the energy stored in spring. In spring. Okay. Now
Okay.
number three. Um, Figure 3.1 shows a shooting competition where air rifles fire soft metal pellets at distant targets. When an air rifle is fired, it exerts an impulse of 0.01 Newton seconds on the pellet. Define impulse. Okay, so what is impulse?
I know it's force times something. I
Yeah.
don't know the meaning.
So impulse is actually the product of force and time. Impulse is the product, so you tell them impulse is the product of force and time, and you show them that I is equals to force times time. You could go ahead, okay? It's just one mark, so I wouldn't advise you go ahead. I thought it was higher, so we could go ahead and explain something, but just say impulse is a product of force and time, then I is equals to F times T. Okay, you got that right?
Yeah.
Okay, the next one is the pellet has a mass of 1.1 times 10 raised to the power minus 4 kg. Determine the speed with which the pellet leaves the rifle. Determine the speed with which the pellet leaves the rifle. Okay, any idea?
We would have used the mass and the impulse to get the time, but we don't have the distance. So how will we get the speed?
Okay. Um, let's see what was given. Let's examine what was given. We have the impulse. Okay, okay. We have impulse, which is 0.019. Remember, I told you that impulse is equal to change in momentum.
Mm-hmm.
Yeah, which is ft is equal to change in momentum is m brackets this.
V2 minus V1. Oh, V
Okay.
minus C over T.
Yeah. Okay. So F and T is impulse. We already have impulse as that already, isn't it? And
Yes.
since the air is fired to a wall, the wall has a velocity of 0 because it's stagnant. Okay. So that means this is 0.019 is equal to your mass. You already have your mass as 1.1 times 10 raised to the power minus 4 multiplied by V. Okay, so V is equal to, so I need you to do that. Your calculator 0.019 over 1.1 times 10 raised to the power of minus 4.
I got 172.73.
Yes, 172.73. Okay, and that is, what is the unit?
Meter per second.
Yeah, meters per second. Okay, any question?
Nope.
Okay, write that. The next one is kinetic energy of the pellet as it leaves the rifle. I think I'll need you to do this one. This is quite easy since we know
Half
kinetic.
K square.
Yeah, half what? What did you say?
I say half K square equals
No,
to
no,
half
no,
MV square.
not half Ke squared. Ke kinetic energy
Oh,
is equals to half mv squared. So you know the mass, you know the velocity. So what will be the answer?
velocity is the same thing as speed, right?
Yes, same thing. Just that one is a vector, the other is scalar. One has direction, the other doesn't have direction. So I'm waiting. What's the answer?
I got 9.5 times 10 raised power minus 3.
9. Are you sure?
0.5 times 10 raised power minus
It
3.
can't be 9, no.
0.009 now.
It can't be 9.
How?
Did you square this 170 squared?
Oh no. Okay, 1.64.
Exactly, 1.64. Okay, 1.64 what? So what's the unit?
Joules.
You said?
Joules.
Yeah, joules. Okay, joules. Okay, the next one, the next one. Okay, are you done writing?
Yes.
Okay. Um, Now, the pellet melts when it strikes the target. Describe how the molecular structure of liquid metal differs from that of solid metal.
That's the difference between liquid and solid particles.
Yes, liquid and solid molecules or particles. But you give your answers in form of molecules. So I'm waiting. So what's the difference between liquid
Um,
molecules and solid
the
molecules?
liquid molecules flow more easily, while the solid molecules are confined in a certain shape or space
Why? That's why we want to know. We know they flow easily. Why?
because they have higher kinetic this thing. I don't know.
Okay. When it comes in terms of molecules, we know definitely that the molecules in between the liquid molecules, um, for example, um, if this, if you see something like this, um, and then you have something like this. So you see that IGCS is actually very easy.
Yeah.
Uh, okay, now, sorry, that's, uh-oh. Now, if you notice now, there's a difference between this and this. The first one, what do you notice about the first one?
There are more spaces between the particles.
Exactly, that's what we want to hear. The molecules of liquid are spaced, are slightly far apart compared to solid particles. This is a solid particle. These particles in solids are tightly fitted together, while the
Mm-hmm.
molecules in liquids are spaced. And because of that, they have irregular arrangements. They have irregular arrangements in liquid. The that's it. I've given you over two differences now that the liquid molecules have irregular arrangement. Liquid particles, the molecules between them are far apart, like they are slightly far apart, and the molecules are not fixed in place. But solid particles, they are fixed in place. They have fixed shape, fixed structure. So that's the difference, and that's why the pellet melts when it strikes the target. Did you get that? Did you get that, please?
Yes.
Okay,
Yes, I did.
all right. Um, okay, the next one, sound wave. I guess this is where you met, right? Okay, are you there?
Yes.
Okay, figure 4.1 shows a loudspeaker that is producing a sound wave in air of frequency 15,000 hertz. Describe how the cone of the loudspeaker produces the sound. Okay, can you describe that?
Hello? Okay.
Sorry?
The stuff was cracking.
Okay, yeah, I said Describe how the cone of the loudspeaker produces this sound.
Amplifies the sound.
No, they didn't ask you what. They asked you how will it produce the sound? How does the speaker produce the sound? Now, one of the things we should
It
know about.
converts
Okay, it converts what?
um electric energy to sound.
Okay, now this is it. One of the things we must understand about sound is that um, anything producing sound, there's one common word between them: vibrations. The
Okay.
fact if you take a speaker and you are playing a music, you put little drop of water, you discover it vibrates. There's a
Mm-hmm.
vibration happening there. So actually, what produces the sound is that, please write this, the neighboring air vibrates. The neighboring air vibrates. The neighboring air vibrates.
I got that.
You said?
I said I got that.
Okay. Neighboring air vibrates, producing compression and refaction. The neighboring air vibrates, producing neighboring air vibrates, producing compressions and refactions. I hope you know what is compression and refactions.
Compression is where like the particles are close together, while refraction is like the space between the
Yeah,
stuff.
exactly, exactly. And that happens majorly in what kind of wave?
Longitudinal.
Longitudinal waves. Okay. When we start having these particles fitted, and then okay, we do understand that. It's all right. Now, the speed of sound in air is 330. Speed of sound is 330 meters per second. We have this as 330 meters per second. The wavelength, calculate the wavelength. Calculate the wavelength. Now remember, they gave us what else did they give us? We have the speed. What else again do we have?
The frequency.
We have the frequency as 15,000 hertz. So what is the wavelength?
0.02
0.022 units.
meter.
Okay, 0.022 meters. Correct. Okay, very easy. Now, loudspeaker. The loudspeaker is placed a considerable distance to the left of a barrier with a gap. The width of the gap is double the wavelength of the sound. Sound from the loudspeaker reaches the barrier and passes through the gap. Whenever you see things like this, what does that tell you?
Um, that was supposed to draw the wavelength and stuff, and that
What
if you
property of
want to
wave is
get
it?
the diffraction,
The diffraction, exactly. Okay, sketch a graph that represents the sound wave as a series of waveforms traveling towards the barrier, number one, traveling in the gap, number two, and traveling away from the barrier. So, and they said the loudspeaker is the width of the gap is double the wavelength of the sound. So exactly what we just need to do is we just
divide the width of the gap by 2 to get the wavelength.
you said
Is it not to divide the width of the gap by 2 to get the wavelength? Because the gap is double the wavelength. Are we not measuring it, or we're just drawing like that?
uh, they said not to scale. So if we could measure. but we know definitely that is not this. The width is more than what we are drawing here, right?
Yes.
The width is more than what we are drawing here. So um, we've just done the. We are doing the second part now.
Do I still have to use a compass?
Um, def at this point, we definitely need that. We definitely need that too. Oh no no no!
Okay.
I think I'll just need to use my free hand here. Uh, already know what to do here. Oh, this is not perfectly straight. Okay, you know what to do definitely that this is not perfectly straight. And then, sorry, we use,
The chicken in your background is making noise.
it has stopped now.
What happened?
Ah,
They want to cook it.
then, okay, so this is it. This is
Wait, do we
near,
have to draw the arrows?
no, just this arrow to show that it's moving. No, um, to show that it's moving from here to this point.
Okay.
Okay, now that was 3 marks. Good. Number 5. Figure 5.1 shows a sphere that is negatively charged. Figure 5.1 shows a sphere, okay, that is
This is electrostatics.
exactly, that is negatively charged. The sphere is attached to a plastic stand. On figure 5.1, draw arrows to indicate the pattern and the direction of the electric field in the region surrounding the plane.
I've not done electrostatics before.
You said?
I've not done electrostatics before, so I don't know
I
what.
think you've done that before.
When.
Yeah, 10.
No, with you.
I think I've done that with you guys also. But nevertheless, with what you're saying there, okay, now draw arrows to indicate the pattern and direction of the electric field in the region. Please, if this goes off, still stay online. I would have to look back.
Yeah, I'll come back.
You understand?
Mm-hmm.
Okay. So what we just need to do is just to draw 4 or more radial arrows. That's just it. Now this is negative here. So um, if you are drawing the arrows outside the sphere, all we just need to do is they said draw arrows to indicate the pattern and direction of the electric field in the region surrounding the sphere. Uh, this is positive, positive.
Somebody say we should draw arrows. Why are we drawing positive?
Uh, the oh sorry. Now this is sphere that is it's already negatively charged. So
Mm-hmm.
draw arrows to indicate the pattern and direction of the electric field in the region surrounding this. So all we just need to do is just to draw um, 4 or more radii arrows, and they should, and at least, okay. So I think what we just need to do is this. Sorry, I think I have to
Are they
use
coming towards the ball or moving away
um
from the ball?
one points towards the center, one um, going down, and okay, okay, okay. All right, we just drawn the arrows. Now the next question says at least one of them should point towards the center of this circle. Okay, and they should point downward. Okay, now the next one is okay, I need to erase this before I go forward. The next one says a smaller uncharged metal S is suspended by a plastic thread and brought close to the negatively charged sphere. Figure 5.2 shows the two spheres. On figure 5.2 indicates the distribution of charge on S. Indicate the distribution of charge on S. So now, since this is a negatively charged, now um, since this is
Eh?
sorry,
Your
this is not
this thing is
negatively.
cracking.
Can you hear me? Can you hear me now? Hello?
Yeah, yeah, yeah.
Okay. Now, since they said this is uncharged. So what we need to do is um, we are going to distribute the charges equally. Positive charge on the left and negative charges on the right. So this is a plastic thread on S. So we just put positive charge and this negatively charged. So if we have three positive here, we must have three negative here. That's all they ask us to do. Indicate the charge of indicates the distribution of charge on S. Now the next question said, state what happens to S. State what happens to S.
It becomes charged.
Okay. It's attracted towards the negatively charged, or it moves towards the negatively charged sphere. Since this is S, since this is S, this is an charged metal, it moves towards the negatively charged S. Why? Why will it move towards negatively charged S? Because it's negative electrons are negatively charged, and electrons flow naturally to they would always flow. I mean, substances will always flow naturally to the electrons, and because the electrons surround atoms. Remember, electrons, when you draw an atom, electrons are always moving, they're always moving outside the atom. So what happens to S in this case is that it moves towards the negatively charged sphere.
This fair.
Yeah, it moves towards the negatively charged sphere. That's exactly what happens to it. The next thing is an F wire is then touched against S. Describe what happens in the wire and state how this affects the charge on S.
Won't it like absorb the charge and then the S will not have any charge again?
Okay, an earth wire. Remember, an earth wire does what? What's the function of an earth wire? It takes the charge downward, isn't it? So
Yes.
an earth wire,
Yes.
when it's touched against S, it takes the charge downward to the ground, and then the charge on S becomes, now imagine, remember the charges on S, this was positive, positive, negative, negative. When an earth wire is touched against S, what happened? This is what happened. The negative follows the earth wire to the ground and becomes what? When it follows it,
Neutral.
not neutral. There's still a
Okay,
charge here.
positive.
Positively charged, exactly.
Positive.
Right? It becomes positive. Do you understand that?
Mm-hmm.
Okay. Have you written that?
Yes.
Okay. So it becomes positively charged. Please, whoever that is just coming, okay, that person has not heard me yet. It's still muted. The next one, the metal sphere S is an electrical conductor. The plastic thread is an electrical insulator. Explain this difference by referring to the structures of the two materials.
Um, what do you mean by the structure?
Yeah, the structures, yes, the structures. For example, S is a metal, this is a plastic thread. Now, and they said something that metal S is an electrical conductor. This is a conductor, S. Plastic thread is an insulator, electrical insulator. So they want us to see what's the difference between um what they're just asking you. The summary is what's the difference between a conductor and an insulator.
The conductor um absorbs electricity while the insulator blocks it.
No, that's not what they need. They said to this, yeah, that's correct. That's a bit correct, not totally correct, but really, that's still not what they want. What they really want is this: you should use electrons. How do you use electrons now? In an why do you think metals conduct electricity?
Good day, sir.
Yeah, good day. Who am I? Who is?
Sir, it's me, Caris.
Oh, Caris, welcome, welcome. We had actually started since. So I wouldn't know.
Sir,
You said?
I had like a problem.
Sorry, what is she saying? You had what?
I